started.
All right, so welcome to week 2 of 11th August, where we are continuing the CS772 course. And I'm going to discuss a few fundamentals needed for deep learning, which are listed here: Perceptron, Sigmoid, Softmax, all these leading to probably the most important algorithm of deep learning, which is backpropagation. I'm also going to discuss your first assignment of the course, which is POS tagging, making use of hidden Markov models, encoder, decoder, and large language models. Now, we'll be I'll be speaking for about 40 minutes, then give you a break for 5 minutes, and then continue for another 40 minutes. So let me begin. Softmax and then POS tagging assignment. Now, one slide recap of lecture 1 of mine, which happened on the first day of the instruction, was touching on the nature of language, where we had some very intriguing properties of human language, namely recursion, etc. We emphasized that NLP is a stacked operation starting from morphology, going through shallow parsing, semantics, pragmatics to discourse processing. In discourse processing, you have a large number of sentences, all coming together to form what is called a discourse. Let's call it discourse. It's a collection of sentences with coherence inbuilt in them. Also, this very important equation, NLP equal to linguistics and probability, where linguistics provides the insight from language science and probability gives a scoring function for choosing amongst various hypotheses. Remember that language is characterized by ambiguity. Words, sentences, phrases typically have more than one meaning. Now, in the context, which meaning is most appropriate? So we have to choose that particular meaning or that particular option. So this is done by probability. And probability itself is computed from data. The more the data, the better is the confidence in the probability. We talked about 3 generations of NLP: rule-based, statistical machine learning based, and then deep learning based. So we will take up problems. For example, POS tagging. We'll look at statistical machine learning based and deep learning based solutions. The rule-based solution, actually nobody talks about these days. It's quite cumbersome. That's why statistical and deep learning based methods. We discussed the meaning of language modeling, the fact that modeling is the other name of prediction. And in language modeling, language elements, language structures, language expressions are predicted. The main challenge in NLP is to resolve ambiguity, which is where machine learning steps in, because machine learning helps you choose the correct option based on the data. Now, ChatGPT and these kind of large language models, especially ChatGPT, has amazing capability. The famous sentence, buffalo, 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 buffaloes, buffalo, buffaloes, buffalo, 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 buffaloes. This sentence, human beings cannot get the meaning of. Well, hardly any human being can do this. But ChatGPT does this. But ChatGPT does this most probably because the sentence has gone into its training data. and it has seen its meaning before. Then we discuss the course information, evaluation, and references. Remember that there are no midsems and there is no midsem and endsem. Instead, just before midsem, there is quiz 1. Just before endsem, there is quiz 2. There is a huge amount of weightage on assignments, which is 40%, and projects, which is 30%. In projects, I'm looking for really creative input from you. You should base your work on 1 or 2 papers, but bring something of your own, some new contribution of your own to the work. And then all our natural language processing work, for which our lab is really very well known, is done in CFILT, which is Computation for Indian Language Technology. Then I presented towards the end our research on rare language phenomena like sarcasm, humble bragging, metaphor, and so on. And also NLP of low resource setting, for example, POS tagging of extremely low resource languages, building of a conversational system in the car AI setting, again, a low resource setting, and so on. So NLP perspective is the following, that there are 3 generations of NLP, which I've already mentioned. Linguistics and probability combined to give rise to NLP, the Buffalo sentence. Now, this particular NLP layer is important because your first assignment pertains to the second layer here, POS tagging, which is sitting on top of the morphology layer. The morphology layer supplies features many times for part of speech tagging. For example, unga as a suffix provides this future tense marking suffix as a feature. And that is sufficient to say that the word is a verb, because this unga suffix applies to only verbs. So this way, each layer builds on the input coming from the previous layer. And in deep learning systems, we have this kind of layers. Transformers, for example, have 6 layers in the encoder, 6 layers in the decoder. So there is this theory that these layers are actually mimicking the NLP stack, but that's a matter of deep research. We saw, to our surprise, that there are essentially 3 tools for NLP. Softmax, which converts a vector of numbers into a vector of probabilities, so thus giving rise to a probability distribution. Cross entropy measures the distance between 2 probability distributions. Typically, this is used in a setting where the target values are known and they form a probability distribution. That means the values sum up to 1. And those values are approximated by a neural network. So the difference between the output from the neural network, which is a probability distribution, and the target probability distribution, that distance is measured by cross entropy. And using backpropagation, we try to minimize the cross entropy and thereby fix the parameters. So backpropagation itself is the epitome of deep learning. When you look at the algorithm and when you look at how universally it is used and how how it is indispensable. Without backpropagation, no algorithm can work. No significant algorithm in deep learning can work. And that is because this gives a way of gradient descent-based parameter setting. We'll spend at least 2 classes to understand how backpropagation algorithm sets the weights. These kind of foundations I'll build in my lectures. And the guest lectures will give you a lot of breadth into what is happening in the deep learning area, what is most recent, most current, what is the cutting edge work that is going on. So both together should give you a very good perspective of deep learning for NLP. Now, starting with the building blocks, the neural networks are built out of single neurons. So initially what came was perceptrons. These are motivated by a biological neuron, where when the input vector is impressed here, it is multiplied by the corresponding weights. That is the dot product of the weight vector and the input vector. The summation sum is compared with the threshold. So if the threshold is crossed by this dot product, then the output is 1, otherwise output is 0. So we say it is inspired by biological neuron. The reason for that is that in biological neurons also, there is this switching on and off of the neurons. So the neurons become on when a particular threshold of the input is crossed. That means inputs come from other neurons and their aggregation crosses the threshold. Otherwise, the output of that neuron is 0. So the same motivation works here, and perceptron as a computational model is proposed. The computational model itself is very simple. It essentially computes a step function. This is the perceptron computational law. Y is equal to 1 if sigma wi xi is greater than or equal to theta. Otherwise, it is 0. And there are tweaks by which you can get rid of the equal to test and have only greater than test. Even less than test is also removed. So let us quickly go over this. This perceptron is can be looked upon as computing a function f, which is the function of the net input. Net input means the dot product of weight vector and the input vector minus the threshold. That is net. Okay, so sigma wi xi minus theta. Y is a function of the net. This perceptron can be looked upon as a function computer. Now, what can you do with this perceptron? You can compute various functions, and one of the important tests of any computing device is whether they can compute the Boolean function. Now, we show this through the AND function, which can be computed by a perceptron. AND function's property is that whenever any of the inputs is 0, the output is 0. Otherwise, the output is 1. So since the output is, whenever the output is 0, the dot product must be less than theta. And whenever the output is 1, the dot product must be greater than or equal to the theta, that is the threshold. So this gives rise to 4 inequalities. When x1 and x2 both are 0, then we get the inequality theta greater than 0. So theta must be positive. If x1 is 0, then W2 must be less than theta. If x2 is 0, then W1 must be less than theta. And if both are 1, then W1 plus W2 must be greater than or equal to theta. So when you have these 4 inequalities, you can see that W1 and W2 being 0.5 and theta being 0.9 is a possible solution. There are infinite number of solutions, and this is a possible solution. So this means we have been able to find a set of parameters. Mark this properly, note this properly. There are only 3 parameters, W1, W2, and theta, but the same principle applies. Even though there are billions of parameters in a large language model, the same principle applies. Our goal is to get these parameter values. Whether it is only 3 parameters in an AND function, or it is billions of parameters in a large language model, the goal is the same. These parameter values have to be found. Now, you can show that XOR cannot be computed because the linear inequalities which are set up are inconsistent within themselves. Okay. So not all Boolean functions can be computed by a perceptron. So XOR cannot be computed because when both inputs are 0, then we have the inequality theta greater than 0. Theta must be positive. And when x1 is 0, then W2 must be greater than or equal to theta. When x2 is 0, W1 is greater than or equal to theta. So far, it is almost like AND, but the last one derails it. When both inputs are 1, the output should be 0, which makes W1 plus W2 less than theta. So you see theta is positive, W2 must be positive, W1 must be positive. How can their sum be less than theta in that case? Okay, and these positive numbers are individually greater than or equal to theta. So that is the inconsistency, and we know that XOR cannot be computed. OR can be computed. So the threshold functions are a very small proportion of Boolean functions. For example, if there is only one input to the perceptron, then there are 4 possible Boolean functions, which are true, false, inverse, and identity. All these 4 Boolean functions can be computed. So all the 4 are called threshold functions. When there are 2 inputs to the perceptron, there are 16 Boolean functions, out of which 14 can be computed by a perceptron. The 2 which cannot be computed are XOR and XNOR. When you go to 3 input perceptron, there are 256 possible Boolean functions, and only half of them are threshold functions. So see how drastically the number falls. For a 4 input perceptron, there are 64K, approximately 64K Boolean functions, out of which only 1008 are threshold. So this number falls rapidly, and we have a proof of this fact that the number of threshold functions is 2 to the power n square. Number of Boolean functions is 2 to the power 2 to the power n. So this is mathematically established, and I'm not going to do it here and give you references. Now, there is perceptron training algorithm, because to be called a machine learning algorithm, you cannot really solve inequalities and set the parameters. The machine learning algorithm changes the parameter iteratively. So fortunately, it so happens that the perceptron also has a training algorithm. And here we have to do some pre-processing. We have to get rid of equal to. Okay, you can look at the slides, how we remove the equal to. Then we observe theta as a weight by introducing a fictitious connection W0, which is equal to theta, and the input is -1. Okay, so you are essentially modeling sigma Wi xi minus theta through this network. Then we negate all the 0 class examples. When this happens, then we are left with only testing for greater than sign. So here is an example for OR perceptron. The 1 class vectors are 1, 1, 1, 0, 0, 1. The output from OR neuron will be 1. For the 0 class, it is 0, 0. Okay, only for 0, 0, the OR output is 0. So we are required to prepend a -1 vector because we are observing theta as threshold. So -1, -1, -1. In the 0 class also -1, 0, 0. Then you have to negate the 0 class, it becomes 1, 0, 0. Now we just have to look for a set of weights W0, W1, W2, such that the dot product of that weight vector with any of these 4 vectors is greater than 0. Okay, you don't have to compare with theta anymore because theta has become an absorbed weight. So very simple now. Just look for a vector iteratively, which when taken dot product with any of these vectors gives the result as greater than 0. So these are the. So then the perceptron training algorithm is simplicity itself. We start with a random value of W. Let's say we start with 0, 0, 0. And for each vector, each input vector in the function, we test for W dot xi greater than 0. If the test succeeds for I is equal to 1 to n, that is for all the vectors, then we return this W as the result. Otherwise, note this is the parameter changing rule. The next W is previous W plus the vector that failed this test. If a vector fails this test, then add that vector to the weight vector. So this is a very simple algorithm, one of the most elegant algorithms, and has very interesting properties. Okay, so to illustrate this, if I take the NAND function, then for the NAND function, we finally have a set of vectors which are these. Okay, 0, 0, minus 1, 0, 1, minus 1, 1, 0, minus 1, minus 1, minus 1, 1. And then we have to find a vector such that W dot xi is greater than 0 for each of these vectors. So step 0, we initialize the W. Let us call this capital W0. Do not confuse with small w0. Small w0 is one of the components of capital W0. So there is the initialization of the weight. Now we see that the first vector itself, 0, 0, minus 1, fails. We add it. And then this new vector fails for x3. We add it and so on. So we go on doing this adding of the vectors. And as we do so, we find that the weights keep on changing. Okay, weights keep on changing. And after a while, when there is a very long sequence of this kind of weight change, we begin to think that maybe it will not converge. But then it does converge, and we see that for NAND function, eventually we have been able to find a set of weight values after 18 iterations. Okay. So I will encourage you to implement Perceptron. This is not part of your assignment, but you can implement Perceptron, or you can take Perceptron code from anywhere, run it on some data, and see the behavior of the Perceptron training algorithm. Now, we are told that Perceptron training algorithm will definitely converge. Whatever be the initial choice of weights and whatever be the vector chosen for testing, Perceptron training algorithm converges if the vectors are from a linearly separable function. Now, linearly separable function we did not define. Linearly separable function are threshold functions or functions which are computed by Perceptron. Why are they called linearly separable function? Because you can separate the two classes, positive and negative classes, by placing a linear surface. Okay, so if you take AND function, then 0, 1, 0, 0, 1, 0 form the 0 class, and 1, 1 forms the 1 class. Then you can put a diagonal, okay, which will cut both x-axis and y-axis and separate the 1, 1 vector from the rest of the 3 vectors. And you cannot do any such thing for XOR, because in XOR, the two classes are diagonally opposite to each other, and no line can separate them. Now, the proof of this statement is given here, which is also an extremely elegant proof. And I give the proof here, which you can go through at leisure, but do take a look at the proof, which is based on formulation of this expression. The GWN, which is a function of the weight value at the nth iteration. W star is the weight which actually separates the data. It exists because we are assuming that the function is linearly separable, divided by mod of Wn. Now, when you process this, you get this expression GWN is W star mod into cos theta, where Wn and Wn cancel each other. Of course, here the assumption is that Wn is not 0. The mod of Wn is not 0. So think about what will happen if the mod of Wn is 0. Can it be 0? It can be 0 only if all the components are 0. So think about why that is or that isn't possible. Now, GWN becomes this quantity, and it is clearly upper bounded by the mod of W star. Then we study the behavior of the numerator of G and the behavior of the denominator of G. We find that as n increases, the numerator of G grows linearly with n, whereas the denominator of G grows as square root of n. So it is very clear that after some time, if n becomes infinity, then GWN also will become infinity. But there is a contradiction here because GWN is upper bounded by W star. You see here, the GWN is upper bounded by W star. So it cannot become infinity, which means that if W star exists, if the function is linearly separable, then the training algorithm must terminate for a particular value of n. That n can be as large as possible, but it will be finite. Doesn't matter how large it is. And the training algorithm will converge even if it is after, let's say, 1 million iterations. Now, this is a discussion on perceptron, which is required as a theoretical foundation, as the starting theoretical foundation for what you're going to do going forward, namely backpropagation and other algorithms for parameter fixing. And architectures like recurrent neural network, convolutional neural network, feed-forward neural network, all of them are based on backpropagation. Now, we move to the sigmoid function. Okay, sigmoid function is a very important function for deep neural networks. Now, a sigmoid function is introduced because we have to make use of what is called multi-layer perceptron, and we have to make use of gradient descent. Okay, but let me not jump the queue. Let me first come to the sigmoid neuron. The motivation is not fully given to you. Let us just say that sigmoid is a probabilistic replacement of continuous function replacement of the perceptron. While perceptron has a step function as the input-output behavior, sigmoid has this smooth derivable input-output behavior. And this smooth derivable input-output behavior is required for the sake of gradient descent algorithm, which is the heart of backpropagation. Now, sigmoid function is of this nature, and sigmoid neuron has this particular expression as the input-output relation. And net I is the dot product of the weight vector at that point and the input vector. The input vector is xi. So 1 plus e to the power minus net I, where net I is nothing but dot product of w and x is the input vector, minus the threshold theta. So this is OI means the output for the ith input. So remember, most of the time the data is given in the form of input and output pair. For example, if it is sentiment analysis data, then we have a vector representing a sentence, and that vector is the input, and for that the output level is 1 or 0 depending on whether the sentence is positive sentiment. Okay, let's say we are not dealing with neutral sentiment at all. We were dealing only with two-class problem. So most of the time the data is given in this form. Taking another example, let's say we have got the data of visa applications and which visa applications were successful. So again, a vector of vector which represents the visa application, and represents the visa application, and the output is 1 or 0 depending on whether the visa was accepted, visa application was accepted or denied. Okay, this is how it is done. Okay, now we have this kind of data typically, and we have 1 and 0, but a sigmoid neuron cannot really compute 1 and 0, because if you look at the input-output curve, then the value of 1 is reached only at plus infinity. Value of 0 is reached only at minus infinity. Otherwise not. So this is how the behavior is. So now sigmoid function is also called the logit function. But before that, there's an interesting story as to how sigmoid function got introduced into deep learning. So apparently, the neuroscientists found that the brain has a way of saving itself from itself in case of extreme agitation, emotion, etc. The neurons just saturate, okay, and they don't send any large signal to any other neuron in case of any kind of disaster situation for the brain. So in case of any extreme agitation, emotion, etc., the brain neurons fire furiously, and that can give rise to some kind of positive feedback, and the number of signals becomes large, and the input coming to a neuron becomes also very large in magnitude. So this is very harmful for the brain because it can lead to coronary, it can lead to brain damage. Okay. So what function can approximate this behavior of neuron? Sigmoid has this property. Okay, it can saturate. Of course, there is no negative signal, but positive signals can saturate after a point of time, and then the derivative becomes very, very small. So hardly any output comes out from that neuron. So now sigmoid neuron we have seen. What is the underlying function? Underlying function is y equal to 1 by 1 plus e to the power minus x. Okay, so this function has an interesting property. The derivative is very simple to compute. Y into 1 minus y, that is output into 1 minus output. Now we can also scale x by k, and then the derivative becomes ky into 1 minus y. You can increase k. As k increases, the sigmoid function begins to go closer towards step function. Okay, and as you decrease k, it becomes more and more flat. Now, sigmoid function, since its output is between 0 and 1, it can be looked upon as a probability computer. Okay, we can say that the output coming from sigmoid is a probability. Probability of what? Probability of the input belonging to a class. If the sigmoid output is, let's say, 0.6, okay, for a visa application, then we say the probability of that particular visa application being accepted is 0.6. And the probability of not being accepted is 0.4. So sigmoid is looked upon as a machine which computes probability. And that's a very interesting and important point. Sigmoid is a probability computer. Similarly, Softmax also is a probability computer. Now, derivative we have already seen. So decision making under Sigmoid, if you take the maximum a posteriori stand, that is, since the output of the sigmoid is the probability of the input belonging to a class, and the output and the 1 minus that probability is the probability of not belonging to that class, the other class, not belonging to that class, but belonging to the other class. Then we say that we make the decision as follows. If the probability of class 1 is more than probability of class 2, then decide in favor of C1, otherwise decide in favor of C2. So if the sigmoid output is coming as for a particular visa application to be accepted as more than the probability of being rejected, then PC1 is greater than PC2. And we know that PC2 must be equal to 1 minus PC1, which gives rise to the situation that PC1 must be greater than 0.5. So that's why we say that whenever the sigmoid function's output exceeds 0.5, okay, then we decide in favor of the that particular class. Okay, just like I said, for the visa application, if the sigmoid output is more than 0.5, we say that the visa application is accepted, otherwise not. So one interesting question is, why restrict ourselves to only 2 classes for sigmoid? If we can divide the sigmoid into small segments and devote each segment to a particular class, then can we solve a multi-class classification problem using sigmoid? So you think about it, it is not possible. One reason is that these probability values will not sum to 1. Okay. Is there anything else you think about it? Okay, so at this point, let me take a break for 5 minutes, and then we'll come back for the rest of the class. The break, this is the slide on which we were. We were discussing the properties of sigmoid function. The fact that it is a probability computer is a very useful thing to remember. Now, sigmoid is used for 2-class classification. What to do about multi-class classification? So for multi-class classification, we make use of what is called the softmax function. So if there are 2 classes, graduating to multi-class involves graduating from or moving from sigmoids or base solution to softmax based solution. So for the ith input and for the cth class, where C is small, C varies over capital C classes. Capital C classes and small c is a particular member of the capital C class. In softmax, we decide for that class which has the highest probability. So again, it is a winner-take-all decision. Whichever probability is larger than others, that particular class gets the favorable decision. Okay, the input is said to belong to that particular class. So an example of that would be if it is a sentiment analysis problem. There are 3 classes, positive, negative, and neutral. Let us call these 1, -1, and 0. Then for these 3 classes, is input, and the softmax function is such that the probability of neutral comes out let's say the values are 0.2, 0.2, and 0.6. The neutral class is 0.6, which is more than the each of the other two classes, and we say that this particular statement belongs to neutral class. Okay, so Delhi is the capital of India is a sentence with neutral sentiment. Now, whether this probability will come out to be correct or not depends on the effectiveness of the training and the quality and quantity of data. Now, let us see what is softmax. Softmax function turns a vector of k real values into a vector of k real values that sum to 1. So input values can be positive, negative, 0, or greater than 1. But softmax transforms them into values between 0 and 1 so that they can be interpreted as probabilities. This is the property of softmax, and it is extremely useful in machine learning situations. So here is the mathematical form. If z bar is the input vector, then sigma is the softmax function operating on that input vector. And the ith component of the output vector after this operation is e to the power zi, where zi is the ith component of the input vector, divided by e to the power zj, j varying from 1 to k, where there are k components in the input vector. And for each component, you raise it to the power e and take these sums and divide e to the power zi to get that particular component. To give an example, if the input vector z is 1, 2, 3, then the first component is 1, second component 2, third component 3. We raise this to the power of e, so e to the power 1 is 2.72, e to the power 2 is 7.39, e to the power 3 is 20.09. You take the sum and put it in the denominator. For the softmax function, the components would be 2.72 divided by this denominator, 7.39 divided by this denominator, and 20.09 divided by this denominator. So we get this vector of 0.09, 0.24, and 0.67, which value is summing to 1. So the softmax is giving me a probability distribution this way. Now, softmax and cross entropy are used together, okay, to solve machine learning problems and training of parameters, taking an observed probability distribution closer to the target probability distribution. So there's an intimate connection between softmax and cross entropy. Softmax gives a vector of probabilities. Winner-take-all strategy will give the classification decision. So this particular example I have already discussed. This is corresponding to sentiment analysis. Suppose the softmax vector is obtained from the example where the softmax vector is 0.09, 0.24, and 0.65. These three values, let's say, correspond to the three classes: positive, negative, and neutral sentiment. So given an input sentence like A, I like the storyline of the movie, positive sentiment. However, the acting is weak, negative sentiment. The protagonist is a sports coach, neutral sentiment. Okay. Now, what the data will give you is the following. So let us note this carefully. The data will not have arbitrary probability values. The data will have only 1 and 0. Okay, hard decisions. So for sentence 1, I like the story of the movie. The vector, probability vector is 1, 0, 0. Positive sentiment definitely, not negative, not neutral. For sentence B, it is 0, 1, 0. However, the acting is weak. And for last sentence, the protagonist is a sports coach. This is 0, 0, 1. Because there is no sentiment involved in this. It is a plain fact being stated. So the training data is presented in this form. Okay, input is the sentence itself. The sentence itself means the feature vector of the sentence. We'll see later how a sentence is converted into a vector through the word embeddings. Okay. And these word embeddings give rise to a representation for the sentence. The output is given in the form of 1 and rest of the zeros for different classes. So the difference between target T and the obtained probability distribution Y is called loss. Okay. This is a very important term in machine learning, as you know. Loss function, error function, these are the terms used to denote the distance between the obtained probability distribution and the target probability distribution. Now, if the vectors do not form a probability distribution, then we have to use what is called the total sum square loss. Okay, and that's a different discussion. I'll show that to you later. Cross entropy is the most frequently, or actually almost always, used loss function for comparing two probability distributions. Now, the cross entropy function is defined this way. This cross entropy distance between two vectors P and Q. P is the target, Q is the obtained distribution, is minus x is equal to 1 to n and k by 1 to c, pxk log 2 qxk, where x is the input and k is the class. Okay, so we have log 2 qxk. Qxk is the probability that x belongs to the kth class. Pxk is the target probability that x belongs to the class k. Okay, and q is the observed probability that x belongs to k. What do I mean by observed probability? There is a probability coming through the softmax function being computed by a deep learning system. So cross entropy loss is summed over all the data instances. That is called the total cross entropy loss. And that is equivalent to multiplying probabilities. Minimizing the total cross entropy loss is equivalent to maximizing the likelihood of observed data. That's a very fundamental point about machine learning. Minimizing total cross entropy loss is equivalent to maximizing the likelihood of observed data. So if somebody asks what is the principle underlying this fact of maximizing the total cross entropy loss, the underlying principle is that we want to maximize the likelihood of the observed data. That is one of the cardinal principles of machine learning. Maximize the probability of observation. This is the MLE, maximum likelihood estimate principle, based on which many machine learning algorithms are created. Now, how do we minimize the loss? There is a systematic procedure. We apply a gradient descent approach. We apply then a backpropagation algorithm to reduce the cross entropy distance. And that involves the derivatives of input-output function for each neuron. Feed-forward neural network with backpropagation is the most important technique for us in this course. Okay, let me repeat this point. Feed-forward neural network with backpropagation is the most important technique for us in the course. So now let's fix a bit of notation. So here it is. Sigmoid neuron, we have seen the output OI, that notation indicates the output for the ith input. Capital Xi indicates the ith input, and small x 1i would indicate the first or 1th component of this input vector. I. Okay. The net is always very important for us, which is w.xi. The threshold is assumed to be absorbed in x0. So there is no separate manifestation of this threshold value. So net I is essentially the dot product of the weight vector and the input vector. Then the sigmoid neuron computes the output by computing this function 1 by 1 plus e to the power minus net I. Softmax function, on the other hand, is very similar to sigmoid neuron, but it is little more complex, right? There are more neurons here, more than one. And the notation is also as follows. The input is like sigmoid. You have capital Xi as the ith input vector. And the output is OI everywhere, except that the components are OI1, OI2, OIC minus 1, OIC, where last C is the last component of the output vector. So OIC is nothing but the softmax function of the net IC. Okay, so the net IC, net I is the net is the dot product for the ith input, dot product of the weight vector and the input vector. And OIC is the cth component of that softmax value. So this is how the output vector is formulated. So let me repeat once more. Xi is the input vector. Capital OI would be the output vector. The components are OI1, OI2, up to OIC. Capital C is the last component. Some important points in the notation. Unless we keep track of the notation, it may become, the whole discussion may become, unnecessarily complex, and you will lose track of main points. So I equal to 1 to n. This means there are n IO pair, input-output pairs. I runs over the whole training. See, so here the index is on the training data instances. The first instance is the is 1, second instance is 2, and so on. J equal to 0 to m, where this m indicates m components in the input vector. So one of the data instances is taken is indexing over the components of the input vector. And then we have k, where k is indexing over the components of the output vector. K equal to 1 to capital C. There are C classes, C components in the output vector. So this is the notation. I for data instances, J for components of the input, K for components of the output. Let us remember this notation. Okay, so essentially what I said before. And similarly, W also has the similar convention. Now, one of the important parameters which we'll have to deal with all the time is the net vector. The net vector is the net input arriving at every neuron. So net I1 indicates the first component of the net vector for the ith input vector, second component of the input vector for the ith input, net I2, and so on. Okay. Now we move to a very important discussion, which is the discussion on derivatives. We understand that our basic algorithm is gradient descent, and which involves taking derivatives. So we should put in place our armory of formulae. the expressions that we're going to use going forward. Derivative of sigmoid is the first derivative we are concerned with. So we know OI equal to 1 by 1 plus e to the power minus net I for the ith input. If you take log on both sides and then take partial derivative with respect to a particular component, okay, of the net quantity. So then we have 1 by OI delta net I, which is equal to minus 1 by 1 plus e to the power minus net I, then by chain rule minus e to the power minus net I. So that becomes equal to e to the power minus net I divided by 1 plus e to the power minus net I, which is nothing but 1 plus 1 minus OI. You can check for yourself. Substitute OI by 1 by 1 plus e to the power minus net I. And then you will see that this is equal to e to the power minus net I divided by 1 plus e to the power minus net I. Then we get delta OI delta net I. That is the derivative of the output with respect to the input of the neuron as output into 1 minus output. So you can, if you look at it carefully, it is the product of two probabilities. The OI is the probability of a class belonging to, probability of a data instance belonging to a class, and 1 minus OI is the probability of not belonging to that class, but other class. There are only two classes. So OI into 1 minus OI is that derivative. So this derivative is very simple, and this is one of the attractions of using sigmoid neuron as opposed to other complicated input-output relation for the neurons. Okay, for example, the Gaussian or some other kind of, let's say, bell-shaped curve, or sine function and so on. So it is the simplicity of sigmoid neurons derivative, the sigmoid function itself, and also the biological viability of saturation, which is at the root of this particular point. What about the derivative of softmax? That's an interesting discussion. For softmax, OIC is equal to e to the power net IC divided by summation of k going from 1 to capital C e to the power net IK. Okay. So you see, this is how the components of softmax function are found. E to the power net IC divided by k equal to 1 to capital C e to the power net IK. Now, this summation is a denominator, introduces complexity in the derivative computation, but not so much. Let us see. Again, we take the log path. Log of OIC is equal to net IC minus log of the denominator. Now, if I take partial derivative with respect to net IC, because this is what we are concerned with, the derivative of the output with respect to the input, then I get 1 by O to the power 1 by OIC, the derivative of output with respect to input equal to 1 minus 1 by this denominator into the expression e to the power net IK, which is coming by chain rule. And this is equal to 1 minus OIC. Then the derivative of the output with respect to input is nothing but output into 1 minus output, which is exactly like sigmoid. Okay, so that's nice. Softmax and sigmoid function are very intimately related. We had remarked that, and that is indeed true. Now, what about the derivative with respect to another component of the net I? That is the net input of another neuron. So in Softmax function, since the net input of all neurons are involved, we have to take the derivative with respect to own input of the neuron and also the derivative with respect to the input of other neurons. Okay, this is a requirement because of the nature of the softmax function. So here we have OIC and net IC minus ln and the denominator. Now you see here we have changed the derivative. The derivative is with respect to delta net IC dashed. Okay, delta I is same. I is the index for the data instance, which will not change. But C dashed is the component. So this C dashed is different from C. We are taking the derivative of the output of a neuron with respect to the input of another neuron. So now this net IC's derivative, unlike before, will give rise to 0. Because it's a partial derivative, okay? So derivative of net IC with respect to net IC dashed is equal to 0. Minus 1 by the denominator and e to the power net I C dashed, which is nothing but minus OIC dashed by definition of the output. And therefore, the derivative of the output of the neuron with respect to the input of another neuron is coming as negative of OIC into OIC dashed, which is again very elegant. Okay. Earlier, the derivative was output into 1 minus output. Now the derivative is own output multiplied by the output of another neuron and a negative sign before that. Okay, so that's quite elegant and is sort of systematically falling in place, showing that sigmoid is a special case of the softmax function. Okay, think about it that when the number of neurons is reduced to only 1, all these expressions will be reduced to the derivative of sigmoid. Okay, do that exercise yourself to see that this indeed is the case. So this is the set of derivatives we are concerned with. Okay, and they're very important for us going for further discussions. Now I'll move to the discussion on your first assignment, which is comparing and contrasting HMM-based, ENCO-DECO-based, and LLM-based POS tagging. So the discussion on the derivatives was over, and we are moving to an important discussion, which is your first assignment. So this first assignment involves, you can see, 3 machine learning techniques: hidden Markov model-based machine learning, encoder-decoder-based machine learning, which is a sequence transformer, and LLM-based machine learning, which is based on transformer and very large number of parameters. Now, let us all first define what do you mean by part-of-speech tagging and what is the tag repository we have to deal with. So part-of-speech is a very important grammatical concept for any language. Part-of-speech, there are parts of speech of 2 kinds of words: content word and functional word. For content word, you have these 3 categories: qualifiers, nouns, and verbals. Nouns and verbs are very large categories. Qualifiers are qualifiers of noun and verb. Qualifier for nouns are called adjectives. Qualifier for verbs are called adverbs. Okay. When you come to function words, it is prepositions, postposition, conjunction, and exclamation. Preposition being the most important category for a language like English. For Hindi, where the order is subject, object, verb, the verb goes to the end, we do not use preposition, we use postposition. So ate with spoon in English becomes chammach se khaya. You see with is coming before spoon, that's why it is called preposition. Whereas se comes after chammach, that's why it is a postposition. Conjunction is and, or, but, etc. Exclamation is o, all these words are called exclamation. So you have two kinds of words, content words and function words. And we'll have to get the part of speech tag repository with respect to this particular background. So the problem statement is as follows. The input is a sequence of words and output is a sequence of labels of these words, which are obtained by a machine learning algorithm processing data. As I said, initial attempt for any NLP problem is always rule-based solution. But in case of part-of-speech tagging, the rule-based solution actually has has gone into oblivion because the machine learning-based solutions are much, much simpler. Otherwise, you have to write very complicated set of rules for part-of-speech tagging. Machine learning-based solution, which is making use of data, is very simple. And the algorithm is also general, as we will see now. So input is a sequence of words, output is a sequence of labels of these words. Now, why is part-of-speech tagging a complex problem? Because there is ambiguity again. Like all other NLP problems, ambiguity is the main challenge in part-of-speech tagging also. So most words have multiple parts of speech. You look at the word close. It has adverb, adjective, verb, and noun, all the four tags as part of speech. So running close to the competitor is adverb. Here close is adverb. Close, escape, qualifying the noun escape, adjective. Close the door, here it is a verb. Towards the close of the play, here it is a noun. So you'll have to disambiguate for obtaining the correct part of speech, and that you have to do from the context. So here, for example, running close to the competitor, running close, running, and then close coming after that is an indication that it is an adverb. Okay, so running fast, for example. So here, fast is clearly an adverb. Since close is a qualifier for running, close is coming as an adverb. Similarly, before a noun, if you have a qualifier, it is typically an adjective. So here, close is an adjective for close, escape, and so on. So these kind of rules are there always in the background, except that we do not write those rules sitting down and carefully formulating them. Instead, we run machine learning algorithm on data, which is annotated, and do part-of-speech tagging. Okay. So where does part-of-speech tagging sit? Sorry. It sits between chunking, which is shallow parsing, and morphological processing. Now, let us take an interesting sentence, to bank. I bank on the river bank. So here to bank, that means to carry out banking transactions. Here bank is verb. I bank, that means I depend on the bank on the river bank. So here this bank is correct bank, and on the river bank is the side of the river. So you see the word bank appears 4 times here. 2 times as verb. To bank. I bank. So these 2 banks are verbs. On the bank Here bank is noun. River bank, bank is noun here. So now, how does a large language model do? Or how does ChatGPT do with respect to part-of-speech tagging of this sentence, which is interesting example of a word being used in multiple parts of speech. So it has here, I asked ChatGPT to produce a constituency parse. To produce constituency parse, the system needs the part-of-speech tags of the words. So 2 has the tag as capital TO. These tags are coming from what is called the pen tree bank tag, about which we'll remark, or during your assignment you will learn that these tags are coming from a standard repository. And bank has NN. NN means noun. The part-of-speech tag of comma is comma itself. The part-of-speech tag is PRP, which means personal pronoun. Bank is VBP. VBP means it is a verb. On is a preposition. Prepositions are indicated by IN. The is indicated by DT as the part of speech determiner. Bank here is noun. Okay, so to bank, I bank on the bank. Here bank is surely a noun. On the river bank. So here you can see bank is noun. Frequency parse tree produced by ChatGPT is totally correct. And all the part of speech tags have come out correctly. So remember this, because you'll have to compare your part of speech tagger with the performance of a large language model. Okay, it could be Claude, it could be Grok, it could be ChatGPT, anything. But you will have to see how far, or is it equivalent to the performance of a large language model. In many cases, it is known that part of speech tagging is done extremely well by large language models, sometimes even better than human beings. That is probably because the large context which is used by large language models to compute the conditional probabilities. All this is based on computation of conditional probability. Now, machine learning based parse tagging makes use of what is called the metaphor of noisy channel. Noisy channel is one where an input W comes in and output is T, which has noise in it. Whatever is really expected from W may not appear as such, but it may appear in some distorted form because of the noise inherent in the channel. Okay, so noisy channel metaphor is very appropriate here because the part of speech tag which will come out given the input sentence may not be fully accurate. We want to make it as accurate as possible depending on the constraints, and may not be fully accurate means that it is passed through a noisy channel. So this is modeled by this conditional probability. Probability of B given A is probability of B into probability of A given B divided by probability of A. This is the Bayes theorem. So probability of B given A is called the posterior probability. Probability of B is called prior probability. Probability of A given B is called the likelihood probability. Now, a key question always is whether we should work with the left side, that is probability of B given A, or should we take the right-hand side? In right-hand side, typically, because of the argmax computation, PA drops. And we have the prior probability and the likelihood probability to deal with. Typically, that is the case. Argmax means you take the maximum, you take that argument which gives you the maximum value. So explaining this now. This is the maths of part of speech tagging. By the way, this maths is applicable whatever with the machine learning algorithm. Could be statistical, could be deep learning, but it is the same maths which is the underlying foundation. So we are looking for T star, the best possible tag sequence given the word sequence. Argmax means that you get that particular T for which the probability value is maximum. Now, since argmax is concerned only with T, we can drop PW from the denominator after applying Bayes' theorem. So we have PT into PW given T. Now, PT can be processed by means of chain rule of probability and Markov independence assumption. We say that a tag at a position depends only on the previous tag. This is called the bigram assumption. So probability of T is probability of T0. T0 is typically the hat symbol. T1, T2, Tn plus 1 is equal to dot, which is the last symbol of the word sequence. And this you can divide by, this you can expand into this expression by chain rule. Pt0, Pt1 given T0, Pt2 given T1 and T0, T3 given T2, T1, T0, Tn given Tn minus 1 and minus 2 up to T0 and so on. After that, we apply the Markov independence assumption saying that Tn depends only on Tn minus 1, nothing else. So we have the product of these bigram probabilities, probability of Ti given Ti minus 1. Whatever the other expression, the likelihood, probability of W given T. So probability of W given T also similarly can be processed by chain rule. Probability of W0 given T0 to Tn minus Tn plus 1. The probability of W1 given W0, T0 to Tn minus 1. W2 given W1, W0 and the whole tag sequence and so on. Now we make an assumption the word is determined completely by its tag. That's a strange expression. Instead of saying the word is determined, the tag is determined completely by the word, we're saying the word is determined completely by the tag. This is a characteristic of what is called the generative model. Okay, in generative model, this is what is typically seen. The observations are as if generated by a random process from below, and the hidden variables are of interest to us. In this case, the word sequence is the observation. The underlying hidden variables are the tags which we want to uncover. Okay, so this approach of obtaining the part-of-speech tag through Bayes' theorem and then decomposing the prior probability and the likelihood probability into its smaller elements, applying Markov assumption. This came from automatic speech recognition, where a sequence of signal values is converted to a sequence of text elements. Okay, there again, we have seen this kind of formulation. And borrowing these ideas from ASR for part-of-speech tagging, the credit goes to somebody called Dr. Jelinek from AT&T Bell Labs. And this actually revolutionized the part-of-speech tagging technology. People are surprised that such a simple data and machine learning based approach, this is nothing but hidden Markov model. Okay, these bigram probabilities and the observation probabilities are nothing but hidden Markov model. So this could deliver so well with such simplicity. Okay, the accuracy of the HMM-based POS tagging was most of the time more than the rule-based system. And the rule-based system took years to create lots of complicated rules. So these probability values actually give rise to this generative model. Look at this diagram. We are interested in part-of-speech tagging of people jump high, where noun is the tag for people, jump V is the tag, and high R or adverb is the tag. So for every tag, now hat and dot are very important symbols. Hat is for the beginning of the sentence, dot is for the end of the sentence. In your data, you will have to put these hat and dot symbols for sentence boundaries. So we have these transition probabilities. Probability of going from hat to N is a transition probability. N to V transition probability. Probability of people given N, this is the observation probability. So you can see this is a generative model because the words are getting generated from the hidden variables and the random underlying process. So in my CS626 course, I come up to this and then delve into the properties of hidden Markov model. You might want to look at my last year's YouTube lecture on part-of-speech tagging. And that will, I think, give you a very nice idea about how hidden Markov model came to be used for part-of-speech tagging. Anyway, so after the generative model has been put in place and the training data is obtained, we compute the part-of-speech tag by means of what is called the Viterbi algorithm. The sentence "brown foxes jumped over the fence." Hat is the sentence starter, and dot is the sentence ender. For each word, you have a column of part-of-speech tags. This is called the trellis diagram. And the problem is to find out the best possible path from hat to dot through this part-of-speech tags, which will give you the highest probability part-of-speech tag sequence. This is the goal. And that is done by what is called the Viterbi algorithm. The Viterbi algorithm is actually computing these transition and observation probabilities and their products. The Viterbi algorithm is an efficient way based on dynamic programming. It's a linear time algorithm, linear in the length of the input sequence. And that's a very nice trick because of the assumption of Markov independence. So this you can read up from the literature, or you can listen to my CS626 lecture. The probability values, transition and observation probability values, come from the data. So transition probability of, let's say, probability of noun given JJ, that means the probability of a noun following an adjective is number of times adjective is followed by noun divided by number of times the JJ appeared. Similarly, observation probability of brown given JJ, count the number of times JJ appeared and count the number of times brown appeared as JJ. Okay, and then this ratio gives you those probabilities. So then you have formed the hidden Markov model. So let me finish today's lecture by concretely describing what is it you have to do. And the assignment is due on 30th August 25. There will be a statement of problem given on Teams also. So this is what you have to do. You have to take the part-of-speech tag data from NLTK. This is for English. This is the repository, and NLTK is a very well-known repository of tools and data for natural language processing. I think you can also make use of Hugging Face. There also you should have data, part-of-speech tag data. Then use HMM, ENCODECO, and any LLM of your choice to compare performance. This is the crux of the assignment. So you'll have to look at the difference in performance and you have to explain it also. So for example, if you find that hidden Markov model is doing very well for nouns and not so well for prepositions. On the other hand, encoder decoder is doing very well for prepositions, but not doing well for adverbs. LLM is doing well almost all the time. So you'll have to explain that behavior. So you can use, note this, pre-written, available, or LLM generated code. We have no problem with that. But you'll have to explain what the code is doing. What is the underlying algorithm? And later you will be asked to implement something innovative and complex on or based on part-of-speech tagging, which will require you to code. But get your, ML and NLP work started by doing this assignment, because part-of-speech tagging is the first task which brings machine learning and NLP together. This is your first assignment, which will be due on 30th August 25. And there are teams of TAs which will examine your work. I think there are groups of 2 people. Okay, so this is what you have to do. So let me end today, and we'll continue next week. And every week, as you know, on Fridays, you have guest lecture, which gives you a glimpse of cutting edge research, a lot of breadth, and I will take care of the depth or foundations. Thank you.